Okay, so today our topic is an example of how to design analog low pass filters. Remember, our task is to design digital IR filter, but I told you several times that there are some problems in designing digital IR filters directly, and what the problem is, that I'll discuss maybe of course today, but there is a reason we have to go back to an equivalent analog low pass filter. We have to design an equivalent analog low pass filter, an appropriate low pass filter, analog low pass filter, and from that we have to derive or this IIR digital filter. Okay, so IIR low pass filter. Now we have discussed the analog signals and systems briefly, but all essential features were discussed. Now we will be considering one rational model, that is, we will design an analog filter which will satisfy certain things, that it should be causal and stable, it should be rational, that is, transfer function will be a numerator polynomial divided by denominator polynomial in S, because we know that this can be realized by using differential equations. Those in turn can be realized using op amps, differentiator, integrator, we know. So, using them. Okay. And then, since a low pass filter, its magnitude response should be ideal, maybe it is some say value 1 or it can be value anything. This is omega, this is mod H A, forget about A, because all are analogs, I am dropping the index A here, or maybe today I require analog and digital both, so I bring back H A, okay, that is not bad. Okay. So, magnitude of the Fourier transform, that is transfer function, Fourier transform the impulse response, take the mod of that, either you square it or keep it as it is. It should be flat within the pass band minus omega c to omega c. Omega c is called the cutoff frequency. Okay. Normally, the transfer function is given both by magnitude and phase. If it is ideal, magnitude should be flat within the pass band, desired pass band of the filter, and frequency and phase response should be linear in omega. But you cannot design to satisfy both, So, what we do, we concentrate on satisfying the magnitude response as much as possible, and then we hope that this phase within this band is somewhat close to being linear, not very widely off linear. So, we will concentrate on this. And what is our purpose? To design an analog rational filter, rational model of this kind, B0 plus B1 S plus dot 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 B Q S to the power Q divided by A0 plus A1 S plus dot 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 plus AP S to the power P, okay, and its frequency response is, which is B0 plus B1 J omega plus dot 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 B Q J omega whole to the power Q divided by, just replace S by J omega. That is, in the S plane, I am now on the J omega axis, vertical axis, Y axis. Okay. This H J omega should be such that its mod square is like this. But you see, this is a very ideal function, it is completely discontinuous here, there is a discontinuity here, up to this it is flat and then suddenly it falls immediately to 0. But this is H J omega, you can see easily, if you take the mod of this, okay, it will be a continuous function of omega. You cannot realize a discontinuous function by this, by taking the mod of this and squaring it up, because that will be definitely a continuous function of omega. Okay, from this expression only you can see, if you take the mod of numerator by mod of denominator and square up and all that, there will be some function of the omega square, omega cube multiplied by some constants and all those things. So, that will be a continuous function. So, you cannot realize a discontinuous function by a continuous model like this, but you can go close to that. You can approximate it by various approximation functions. One of them is called Butterworth, and we will be discussing that. Okay. Here, what happens? You try to approximate this function, this is the desired function, by this. This should be rational, okay, because H A j omega is rational. So, So, if you take mod of h h omega, there is mod of numerator by mod of denominator and all that, and if you square up, it will still be rational. Okay, B0, B, I mean, there will be powers of omega and denominator also powers of omega. Okay. So, this will be rational, but the function that we are using, that is called Butterworth function. For this h j omega will be a particular type, so that when you take the mod square, it will be 1 plus, and mod square means it will be real, because you are taking mod. So, obviously, it will be omega by omega c, suppose whole to the power 2n, where n is an integer. What is the meaning here? If omega is less than omega c, then omega by omega c is less than 1 whole to the power 2n. Now, if n is large, some quantity whole to the power 2n will be very small as compared to 1. So, you can neglect that, its value will be 1. So, for all omega in this range less than omega c, okay, omega here, you will see its value is close, I mean its value is almost 1. On the other hand, if omega crosses omega c, then its value, if omega is less than omega c, we know its value is less than 1. Okay, I repeat it. So, that raised to the power 2n will be much more less than 1. So, you can ignore that as compared to 1. So, 1 by 1, 1 this side. On this side, if omega is greater than minus omega c, so omega by omega minus omega by omega c on this side, omega is negative. So, there will be this ratio will be negative, but its magnitude will be less than 1 if this happens. If omega is somewhere here, then omega is greater than minus omega c. So, omega by omega c, this ratio will have minus sign, but minus to the power 2n, minus will go, because it's an even number 2n minus something whole to the power 2n. So, minus has no meaning, because minus when raised to an even power 2n, it will become plus, and omega by omega c magnitude is less than 1. So, again the same thing will happen, its value will be so less as compared to 1, you can ignore it, and so 1 by 1 it will be 1. So, for up to this maybe its value will be 1, and then for omega greater than omega c on this side, omega by omega c will be somewhat greater than 1, and that raised to the power 2n will be much higher than 1. So, then 1 you can neglect, and it will be 1 by omega c whole to the power 2n, and as omega increases, this quantity then starts increasing very much, and this is the denominator. So, 1 by this, and this is much greater than 1. So, this ratio becomes much less than 1. Okay, and as omega increases, finally it goes to 0. That is, first once omega crosses omega c, omega by omega c is say somewhat greater than 1. So, that to the power 2n, if n is large, will be much higher than 1. So, forget 1. 1 by this, and this is greater than 1, and raised to the power 2n much greater than 1. So, 1 by something much greater than 1, it will be very close to 0, and as omega goes on increasing, finally it will go down to 0. And at omega equal to omega c, it is 1. So, 1 plus 1 to the power 2n, 1 to the power 2n is 1. So, 1 plus 1 by 1 plus 1, that is 1 by 2. So, that means it will be a function like this. As omega increases, it will fall, but always for any n is called the order of the Butterworth filter, order. For any n, it will cross through this. That you get from this expression. For any n, omega equal to omega c means this is 1, 1 to the power 2n is 1, 1 plus 1, 2, 1 by 2. This is 1 by 2. But as n increases, it becomes sharper. It becomes like this. So, this is rational, because capital omega, its power is there 2n, capital omega to the power 2n. There are intermediate powers like omega to the power 1, omega to the power 2, omega to the power 3, they are absent. That means the corresponding coefficients are 0. But at least it is a polynomial in omega, because 1 is there and then omega to the power 2n, that is there. So, it is rational. Okay. Now, how to realize it? Making sure the corresponding HAS from which this H j omega has been obtained by replacing S by j omega, that HAS is not only rational, it is causal and stable also. And then its frequency response will be this, which almost approximates this very well, and it serves my purpose. All right. For this, we see certain things. HA this is mod H j omega, that means H a j omega, sorry, into H a star j omega, right. Mod z square is z into z star, this equal to this. What is H a star j omega? Now, for that some basic properties, you may have forgotten very basic properties of complex numbers, that is, if you have got one number z 1 another by z 2 and z 1 equal to say r 1 e to the power j theta 1, z 2 is r 2 e to the power j theta 2. Okay, if the overall thing is conjugated, that means r 1, this will replace z 1 and z 2 by this, you have r 1 by r 2, this is the magnitude now, e to the power j theta 1 minus theta 2 conjugate, which means r 1 by r 2 e to the power minus j, if you have a minus where, minus j theta 1 plus j theta 2. Okay. Which means you can write it as r 1 e to the power minus j theta 1 divided by r 2 e to the power minus j theta 2. When it goes up, it becomes plus, which means z 1 star by z 2 star. That is, star of a ratio of two complex number, conjugate of a ratio of two complex number is same as, first you take the conjugate of the two complex numbers separately and then take the ratio, you will get the same thing. That is one property. Another property is, if I have got a z and z is raised to the power, is raised to some integer power say n, and then if you take conjugate, z is say r into e to the power j theta, so r e to the power j theta whole to the power n, then conjugate, what is it, r to the power n and e to the power j n theta, after conjugation it is e to the power minus j n theta, which is also same as r e to the power minus j theta whole to the power n, or to the power n e to the power minus j theta whole to, but this is z star. So, z star whole to the power n. So, if you raise a complex number to some power n and then take conjugate, you will get the same thing if you first take conjugate and then raise it to the same power. So, here H H omega is a ratio of two complex quantity on numerator and denominator. So, conjugate of overall H star j omega will be ratio of the conjugate of numerator by conjugate of denominator, right, because of this fact. If you call the numerator z 1, call the denominator z 2, z 1 by z 2 whole star is same as z 1 star, there is star conjugation of the numerator divided by conjugation of the conjugate of the denominator. If you have conjugate of the numerator and then all the coefficients are real, b 0, b 1, b q, that are real, we are assuming a 0, a 1, a p are real. So, b 0, so conjugate of a summation of this also you know, z 1 plus z 2 star, z 1 plus z 2 star is same as z 1 star plus z 2 star. How to show that? It is very easy. Whenever you have plus or minus, go for the rectangular form, that is z 1 is a 1 plus j b 1, z 2 is a 2 plus j b 2. Whenever you have product or division, go for polar form. So, a 1 plus j b 1 plus a 2 plus j b 2. If you add a 1 plus a 2 is the real number, real part, j into b 1 plus b 2 is the imaginary part, then conjugate. So, it becomes minus j within bracket b 1 plus b 2. You will get the same thing, a 1 minus j b 1 plus a 2 minus j b 2, you will get the same thing. This is very easy. So, conjugate of the numerator divided by conjugate of the denominator. Conjugate of the numerator means conjugate of every term, because of this conjugate of z 1 plus z 2 is same as conjugate of z 1 plus conjugate of z 2. You can extend it to any number of terms in the summation. So, numerator conjugation means b 0 conjugation, but b 0 is real. So, b 0 remains as it is. Then b 1 into this conjugation. Conjugation of a product is product of the individual conjugated quantities, but b 1 is real. So, b 1 remains as it is. J omega, its conjugate becomes minus j omega, dot 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 b q, j omega whole to the power q. I told you any complex number raised to some power say q and then star, it will be same as first you conjugate it and then raised to the same power. So, first you conjugate it minus j omega whole to the power q, divided by same way conjugate of a 0, that is nothing, a 0 only. Conjugate of a 1 j omega, there is a product of conjugate of a 1 into conjugate of j omega, but a 1 is real. So, a 1 remains as it is. Conjugate of j omega is minus j omega, and like this again a p into j omega, conjugate of the product means first you conjugate a p, but a p is real, so as it is j omega whole to the power p, there is a p here. J omega whole to the power p then conjugate is same as minus j omega, but this first you conjugate then p. This is the thing. And you will see this is same as if in the original h is j omega, instead of j omega if I put minus j omega everywhere. J omega minus j omega, j omega minus j omega, j omega minus j omega, j omega minus. So, if the coefficients are real, then h a star j omega is same as h a minus j omega, which means this can be written as not only this as h a j omega into h a, not only star, I can write as h a minus j omega. All right. So, I have got is equal to our chosen approximate function, our chosen function which approximates that original characteristics nicely, this. All right. But this I can also write as, see, h a j omega is nothing but h a s with s replaced by j omega, and h a minus j omega is again h a s, say h a minus s. If I put everywhere minus s, say it is not complete yet. So, let me write h a minus s. So, wherever I have s, it becomes minus s, p 0 plus b 1 minus s dot 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 b q minus s whole to the power q divided by a 0 plus a 1 minus s. Right. H a s I had, I am just replacing s by minus s, so just this. And then if I replace s by j omega, what I get? B 0 plus b 1 minus j omega, b 0 plus b 1 minus j omega dot 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 b q minus j omega whole to the power q, b q minus j omega whole to the power q divided by a 0 divided by a 0 plus a 1 minus j omega, because s is replaced by j omega. So, 1 minus j omega, a 1 minus j omega dot 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 a p minus j omega whole to the power p, a p minus j omega whole to the power p. That means, this quantity which is h a minus j omega as well, this is nothing but h a minus s, then s replaced by j omega. So, h a j omega, h a minus j omega, this product I can write as h a s and h a minus s, in both cases s to be replaced by j omega. Here by this, and here of course h a s, this you replace s by j omega, you get this. So, that is why I write in the form of minus s, so that for both it is the same thing, s equal to j omega. If I write it as h a s, then for this it should have been s equal to minus j omega, and for this s equal to plus j omega. I want s equal to common, s equal to plus j omega for both. That is why instead of s I made it minus s. So, this quantity is this. From this, but this I can write as j omega by j omega c, so j and j cancels. Okay. So, h a s into h a minus s, which is a function of s, there if I replace s by j omega, I get this. So, what is this function h a s into h a minus s? So, that s replaced by j omega, I will get this. So, that means instead of j omega, I should have had s. There only if I replace s by j omega, I get this. That is, I am going backward. What should be h a s into h a minus s, so that when I put s equal to j omega in this function, overall function, I get this. So, identify where is j omega, here is j omega. So, that means earlier I had s there, then there only I replace s by j omega, everything else remains same as it is. So, I got this function, right, which means h a s into h a minus s, I can now say it will be s by j omega c whole to the power 2n. Okay. All right, because now if you put s equal to j omega, you get back this. This is the left hand side, you put s equal to j omega as here, right hand side also is equal to j omega, you get back your original Butterworth function, right. Now, one thing we will see from here, suppose h a s, which is a numerator polynomial by denominator polynomial, in short I write as n s by d s, n for numerator, d for denominator, and if factorize the denominator polynomial, suppose I get one factor separately, s minus something, maybe alpha, and the remaining part I multiply, and it is a polynomial again, so I call it d prime s, 1 degree less as compared to ds, because s minus alpha one particular factor has been taken out, n s remains as it is. So, s equal to alpha is a pole. So, one pole I am examining, so I am taking one factor out, remaining ones are in d prime s. So, there is a pole at s equal to alpha. How about h a minus s? If in this function I replace s by a minus s, so n minus s divided by minus s minus alpha here, and d prime minus s. So, this factor now, earlier it was giving a pole at s equal to alpha, now it will give a pole at s equal to minus alpha. Okay. So, which means if h s has a pole at s equal to say any value, say j alpha, h a minus l will have a pole at minus alpha. Okay. Now, let us consider this denominator. It is a 2nth order polynomial. Okay. It is a 2nth order polynomial. What are the roots? Because we find out the roots, and from the roots only we get, if there will be 2n number of roots, say alpha 0, alpha 1, alpha 2, alpha 3, so we will have s minus alpha 0, s minus alpha 1, s minus alpha 2. Okay. Those will be the factors. So, what will be the roots? So, to find the roots, you take this equate to 0, which means minus 1 whole to the power 1 by 2n. 1 goes to this side, minus 1, so 1 by 2n. Now, minus 1 you can write as e to the power j pi, and then e to the power j pi plus 2 pi, e to the power j, there is e to the power j pi plus 2 pi, pi plus 3 pi, pi plus 4 pi, like that. Okay, pi plus 2 k pi. You will have the same thing, e to the power j pi is minus 1, then e to the power j pi plus 2 pi, there is 3 pi, that is minus 1, e to the power j pi plus 4 pi, 2 into 2, that is minus 1. Okay, dot 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 dot. So, similarly k can be minus 1 also, pi minus 2 pi, that is e to the power minus j pi, that is minus 1, then pi minus 4 pi, so e to the power j minus 3 pi, that is minus 1, dot 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 dot. Okay. So, k can be plus minus 1, plus minus 2, dot 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 dot. Okay. That is minus 1, and then you have got 1 by 2n. Okay. This means there will be various poles for each value of k, there is a root. Okay, k can be 0 also, k can be 0 also, because if it is 0 still it is minus 1, right. So, you have got the roots are s equal to j omega c times e to the power j 2k plus 1 pi whole to the power 1 by 2n, where k was 0 or plus minus 1, plus minus 2, dot 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 dot. Okay. This j is to the power, j is nothing but e to the power j pi by 2. So, this also you can write omega c e to the power j 2k plus 1 by 2n pi into the power j pi by 2. This is just an offset. This is independent of k. So, whatever phase you get, every phase for every k gets added with pi by 2. This is just pi by 2 additional rotation of a phasor. Okay. So, here you will see k will have 0, if you take k positive case, k will have 0, 1, dot dot dot, up to what? It will be up to 2n minus 1, because the moment it is 2n, okay, you will get back the same thing. 2n, I mean, if k is 0, whatever k you had for k equal to 0, that will come up. What you have for k equal to 0? It is the power j pi by 2n. Then it is the power j, like, you know, if you consider this factor, it is the power j 2k plus 1 by 2n into pi. So, k equal to 0. How much it is? It is about j k pi by 2n. K equal to 1. How much it is? It is about j 3 pi by 2n. Dot 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 dot. How far it can go to? It can go up to k equal to 2n minus 1. It is about j. If it is 2n minus 1, how much will it be? 2 into 2n minus 1. Two into 2n minus 1 plus 1 by 2n into pi. This is k. So, 2 into 2n minus 1 plus 1 by pi. Why? Because up to this, because the moment you go to next one, 2n, it will be to the power j, to the power j 2 into 2n, 2n into 2 plus 1 by 2n pi. And you see 2 into 2n, 2n 2n cancels, to the power j 2 pi, that is 1. So, you are left to the power j pi by 2n, which is this. So, you get back k equal to 0 case. This is nothing but this case. That is why you get these many distinct roots. How many roots? 2n roots. Obviously, 0, 1 up to 2n minus 1. And obviously, because your polynomial had a power of 2n, right? This polynomial is a power of 2n. It is a polynomial. Intermediate powers are missing. S to the power 1, S to the power 2, they are missing. So, S to the power 2n, and this j omega c will give rise to a coefficient only. So, it is a 2nth order polynomial where all intermediate terms are missing, only s to the power 2n is there. And if you factorize it, you will have how many factors? 2n factors. That is, if you take the roots, there will be 2n number of roots. Okay. So, these are the roots. All right. How are the roots located? This is S plane. You see, all the roots are a typical complex number of the form r into e to the power j theta. R is this part omega c, and rest is e to the power j into some angle plus into e to the power j another angle. So, e to the power j or some angle. So, all the roots are on a circle in the S plane, and circle of radius, this radius is omega c. What are the roots? You start with k equal to 0. So, e to the power j pi by 2n plus pi by 2. So, pi by 2n may be this much, and then pi by 2. So, it will be here. Next root will be k, if k goes up by 1. So, it will be 3 pi by n, 3 pi by 2n, pi by 2n plus pi by 2 was here. Okay. Next one, if I jump, how much will be the gap? Earlier I had pi by 2n, now for k equal to 1, 2 into 1, 2 pi by 2n. So, pi by n, there will be a gap of pi by n. Are you following me? First start with k equal to 0. So, pi by 2n, this is smallest amount, and then add it, you add pi by 2. So, instead of here, you go here. Then next pole, what will be the angular separation if you go for k equal to 1? So, it will be 3 pi by 2n plus pi by 2, and earlier I had pi by 2n plus pi by 2. So, how much is the gap? 2 pi by 2n, that is pi by n. All right. So, there will be next pole will be here, pi by n. This much is pi by 2n, and there will be poles like this on this side also. There are some interesting properties of these poles that we will discuss in the next class, that will give rise to the Butterworth function. Thank you.